Conservation of energy. Whooshing. Okay, so throughout this unit, we've been talking about energy. We started talking about work and how if you do work, acting with a force over some displacement with a cosine component there, you can change the kinetic energy of an object. And we knew that the kinetic energy was equal to 1/2 mv squared. Then what we've most recently been talking about is this idea of potential energies. Gravitational potential energies, if you lift an object up, or a spring potential, if you like compress a spring or you stretch a spring or a rubber band out, you are storing some energy in it. And these potentials for gravity was like mgh, and for an elastic or a spring, however you want to write it, that was like 1/2 kx squared. Well, what we're going to be doing now is thinking about the idea that if I give something a potential energy, and I've stored energy at this position for the object, if I let go of it, I could drop it. And that potential energy will transform into a kinetic energy. Because I'm not moving, but now I am. So it's a pretty basic idea there. If you've ever been at the top of a hill and you've all of a sudden decided to ride a bike or a skateboard down it, and crash and tumble at the bottom, like, you have transferred energy as well. You've conserved energy here. So that's what we're going to be talking about. Now, one of the terms that we need in general when discussing conservation of energies is we need some way to think about total energies on a system. And what we call that is a mechanical energy, which we designate with a capital E. That is mechanical energy. Sometimes you'll see some people, like myself, write ME for mechanical energy. It's the same thing. But all a mechanical energy is it is a energy of motion and position. And if we kind of think about that definition there, the energy of motion and position, well, the energy of motion was kinetic energy. The energy of position were potentials. So what this pretty much alludes to is that we can think of mechanical energy, this E, as being a combination or an addition of both a kinetic energy plus a potential energy. And some people write this K plus U, like I've just done. Some people write this U plus K. And then, if you wanted to, you could technically write this as kinetic energy plus potential energy using KE and PE if that's more comfortable than using Ks and Us. So however you want to slice this bread, it is still tasty. Okay? And this is the idea of a mechanical energy. It's the total energy of a system given by its motion and its potentials. Now, if only conservative forces are acting on a system, the total mechanical energy is a constant value. And what we mean by conservative forces are forces where you're not going to lose any energy. You're not going to lose any energy to something like friction. Friction is a non-conservative force. If you are sliding on the ground and there's some friction, not only is your body getting some road rash and your skin getting ripped up, but you're losing energy you're not going to get back. Okay? On a conservative force, if I move this stack of sticky notes up, I've done some work on it, but I can get all of that energy back by letting go. And when I let go, that potential switches to a kinetic. I get it all back. So on conservative forces, you don't lose anything. It's just changed how you've stored it. So in this case, the total mechanical energy on a conservative force system, such as gravity, is constant, which means that the change in mechanical energy equals 0. Now, one other way we could write it, that this change in energy equals 0, is we could say that the initial kinetic plus the initial potential equals the final kinetic plus the final potentials. And if we wanted to expand this even further, we would get this extremely long equation right here. Now this equation looks extremely long, but this equation is actually just the equation up here, delta E equals 0. What we've done here is we've said, look, in initial kinetic energy, that is just 1/2 mv squared. That is kinetic energy. Initial potential energies could be gravitational, or they could be spring, or they could be both. So we've included a gravitational potential energy and a spring potential energy, the 1/2 kx squared. This is equal to the final sides of things. Now, normally we've been writing F's in this class for finals and I's for initials, but we are going to be writing a lot of initials and finals. What's actually a little bit faster is to use a shorthand notation in the world of physics. For our final kinetic energy, we'll say 1/2 m, but we'll call this v prime squared. That prime there, it just means the final. It does not mean a derivative. Okay? It is not a derivative. If you're out there, it's not a derivative. It's just a quick shorthand saying this is the final. This is the mgh prime for the final potential energy. This is the 1/2 kx squared prime for the final spring or elastic potential energy. If you don't like writing these primes for the final and nothing for the beginning, you can still write initial and final. There is nothing wrong with that. We're just going to be doing it a lot, so maybe we want to save ourselves some time. You'll see as I go through this, I'll probably go with initials and finals. Sometimes I'll switch it to primes and nothings. Like, you just get used to doing it every single way under the sun. You just get used to it. So whichever way you like to do initials and finals or nothing and primes, doesn't matter. Whatever way is most comfortable, that's what you want to go with. Okay? Now, when we apply this equation, this conservation of mechanical energy equation, there are some interesting things that pop up with it. While the left-hand side of this equation is all of the initial values, what's happening initially in the problem, and the right-hand side is like the final, the after side of the problem, some of these terms might not be there. And what I mean by that is if you take an object like this sticky note and you drop it, there's not a spring right here. So you don't care about the 1/2 kx squared. You simply do not use it. If you have an object moving just to the left and the right, well, your gravitational potential energy hasn't changed, have you? Your initial height relative to some reference point is the same as your final height relative to some reference point. So if you're not changing heights, you don't care about the mgh terms. They just wipe out. So because of this, even though we do have a lot of things there, we might not be using all of them in every problem. And furthermore, sometimes when we do use something, it might go to 0 anyways. Like when we reach our reference position for our potentials. When we are at our reference position, we know that our heights and our displacements are going to be 0. If our velocity, we've come to rest, then our final velocity, our final speeds are 0. So the kinetic energy has gone away. So depending on what's going on in a problem, some of these values might just go to 0, or we might ignore them completely. But this long equation, all 6 pieces of it, is the entire thing if we have a problem where objects are moving and going up and down, like on a hill, and they're hitting and bumping into springs. Okay? So that's the big thing, but it can whittle down. Okay, so let's take a look at how we can apply this conservation of mechanical energy equation, this big long one right here, in the center of that sheet, into a problem. So in our example here, we're looking for the speed of a block. We have a 1.7 kilogram block, so that's our mass, and it's at rest on a vertical spring, which has some spring constant, 955 newtons per meter. Initially, the spring is compressed 4.6 centimeters, so that's 0.046 meters, and the block's held at rest. What we're going to do here is we're going to release this spring. The spring's going to push apart. The block's going to fall due to gravity as well. And we need to try to figure out what is the speed of the block when the spring has returned to an equilibrium position. So this looks like a lot, but in reality, this is a pretty straightforward thing for us to try to tackle. And we'll first start tackling this by drawing a picture. We always draw pictures. Great-Grandpappy Botzer told us to draw pictures, and that's what we're always going to do. Okay? So, let's just draw a ceiling first so we can put the spring on something. And we're not the greatest drawers, but we do our best. So here's our curly spring, and here's a block at the bottom. Now, this position right here, which is a poorly drawn series of dots, this is our initial position right here. Our block is going to be pushed down by the spring and pulled down due to gravity, and it's going to wind up down here. Okay? So that's our initial. On our final, this is going to be pulled out a little bit, and our block's going to be down here. We know that the compression that the spring currently has, how much it's been compressed up, we know that this is 4.6 centimeters or 0.046 meters, if we want that in a slightly better SI unit. Now, if we go ahead with this picture here, and we just write out that big, long equation. I know it's a big, long equation, but it's helpful to write it out because it'll give us an idea of what we need to be thinking about. So we're going to have 1/2 mv squared plus mgh plus 1/2 kx squared. Those are all my initials. And this is going to be equal to 1/2 mv prime squared, that's my final velocity squared, plus mgh prime plus 1/2 k x prime squared. If I'm taking a look at this equation and our picture, since I have these potential energies here, I need to designate a reference position. Some reference position needs to be set so that we can measure heights relative to that reference. Now, technically speaking, it doesn't matter what your reference position is, but once you set it, it needs to remain at that position. Now, in this problem, there is a slightly clever reference position to pick, and it happens to be this final position. I guess the initial position works just as well, but the final position is very nice because if the block reaches this final position, then our height of the block above this reference position is 0, and that term will go away. If we also think about the 1/2 kx squared, the spring potential energy, that needs a reference position as well. Well, that reference position is based off of where the spring is at rest. And this final position here is when the spring is no longer stretched or compressed, it's just where it should be, which means that this final position has an x value here of 0. It's at rest. So this goes away as well. So just by setting those reference positions, we've gotten rid of 1/3 of all the different things in this problem. Furthermore, we know that initially in this problem, the block is just being held at rest, which means that our initial velocity is 0. And that velocity gives us a kinetic energy, which means that this initial 1/2 mv squared goes away as well. So even though we initially had this very long equation with 6 parts, just by drawing a picture, setting some reference positions, and recognizing what we had, we got rid of half of the things just like that. So now if we dive into this and we start throwing in our numbers, we can actually solve for what is this final velocity of our block after it has been pushed by the spring and fallen due to gravity. So let's just throw in some numbers here. We've got mgh, and our mass here is 1.7. Gravity is naturally our classic 9.8. And the height above the reference position is 0.046 because it's above there. That's going to be a positive h value. We can add that to 1/2 times the spring constant of 955. And then this x value here is how much the spring has been compressed, which is the same as the height it's been raised. Don't forget your square on that. Everybody always forgets a square. It gives them weird numbers. And then this is just equal to 1/2 times the mass of 1.7 times the final velocity, or v prime, squared. And now we just have to shuffle numbers around until we solve for that final velocity there. Luckily for us, this isn't too bad. Everything here in green on the left side of our equation are initials. Those are all numbers. We can just pull out our calculator that we've had since our own junior year of college in high school to crunch all these numbers through. So 1.7 times 9.8 times 0.046. I get for the gravity 0.7, we'll round up, 0.77. The 1/2 times 955 times 0.046, and that value squared, so please remember to square the 0.046 first and then work from there. I get 1.01. That's going to equal 1/2 of 1.7 v squared. Look at that, I just wrote vf. If I add the 1.01 and the 0.77 together, I get 1.78. And this equals, if I put the 1/2 and the 1.7 together, I get 0.85. And then if we want to get this VF by itself, we divide by 0.85. We should get something around 2-ish, it kind of looks like. So 1.78 divided by 0.85, 2.09. That equals VF squared. And we've done this enough times to know that if you want to get rid of the square, you take the square root. And the square root of 2.09 gives us a final velocity here of 1.45, if we round up, meters per second. And that's it. That's how we start thinking about and then solving through these conservation of energy problems for conservative forces, where we're not losing energy anywhere throughout the problem. Okay? We drew a picture because that's how you do physics. You start by drawing terrible pictures that are good enough to get you through the problems. We took that picture and we mapped it into an equation. We saw that we lost a bunch of things due to reference positions and initial conditions like not moving. And then we were able to put in our numbers, work them through with algebra, and then get a final answer. Okay? So this problem is finished. We'll take a look at another practice problem next, and then we'll start looking at how this changes slightly when we do lose some energy due to friction. But until then, adios, and take it easy.